And so, guys, here's the scoop for today. This is all review. Assuming that you had me or Miss Call for chemistry last year, this is all review. And the reason that I can say that with assurance is because all I did, guys, was took the notes from General Chem and condensed them significantly into what we're going to go over today. So guys, we're going to do energy levels and sublevels and orbitals and spins and 1s2, 2s2, 2p6, 3s2, 3p6. We're going to pull all this stuff together right now. But guys, you learned all of this last year. So I am going to teach all of this through the lens of review. And to be honest with you, most of my students go, oh my gosh, I learned so much today, because while last year I was functionally able to do what I was being asked to do, you could do the 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p game, you didn't really understand what you were doing. So guys, I think for most of you, you're going to have sort of this aha moment where you're like, oh my gosh, I didn't see that before. But guys, if this stuff is not fresh in your memory, we're going to let Hank Green take a swing at it first.
Hello, I'm Hank Green.
So guys, you may remember these videos from last year. When we introduced this material to you last year, we did it by showing you a series of Hank Green videos. And last year, you may remember that I explained to you, if you were my student, that the only intent in watching these videos was frankly to plant seeds and create confusion. This shouldn't be the case for you today, as he starts talking about probabilities and the wave-particle duality of nature and orbitals being the boundaries of wave functions and all of these interesting ideas we've been talking about. Guys, this should ring true with you. So I'm going to give you a second to is the jumping off point, at which point we're going to review everything that you should remember about this stuff, and then we'll ask questions, and then you'll have time to work on homework. So, without further ado, I give you Hank. He's a fast talker. I don't think he breathes.
Hello, I'm Hank Green. Welcome to Crash Course Chemistry. Last time we left off with Mendeleev believing he had discovered a cosmic mystic reality about the world, but in fact, he had discovered the effects of his worst enemy, tiny, invisible particles. Electrons, which are so marvelous and peculiar that it wasn't until 80 years after Mendeleev's first periodic table that they were really understood by anyone, and to this day, still very, very few people understand them. But in like 10 minutes from now, if all goes according to plan, you will be one of those people. So let's do this. In 1865, before Mendeleev published his first periodic table, a young chemist and activist, Jon Newlands, published a paper on the periodicity of elements, comparing their repetition, at least the first two rows of it, to a musical scale.
Do you guys remember this video from last year where they talk about the octaves and likening them to music and stuff like that? And I know some of you have real rich musical backgrounds. Guys, it's interesting as you get further into your pursuits in chemistry and physics, and you actually start to talk about octaves and resonance, octet rule, right? Octaves and resonance and harmonies, and you talk about that stuff in physics and chemistry classes. It's really kind of fascinating.
All do, re, mi, fa, sol, la, ti, do and stuff. Maybe, he theorized, lithium was just sodium, but an octave higher. Maybe they were, in a sense, the same note.
And you made that connection, right? Lithium and sodium are in the same group, so they react the same.
He delivered this idea to the Royal Academy, the most prestigious group of scientists in the world, and they basically laughed him off the stage. Music is art, and chemistry is science. Now, describing science in an artistic way might be a fine parlor trick for helping little babies or women understand the work you do.
Remember that? Yeah, guys, they actually thought that way, like less than 100 years ago. Crazy world.
But they have no place in the Royal Academy. That's my impression. But there was no way, of course, of knowing that it turns out that Jon Newlands, when it came to the actual functional physical reality behind the periodicity of the elements, was more right than any of the scientists who laughed him off the stage that day. And I never got to find out how right he was. We didn't discover that his analogies were barely analogies until long after his death. But it turns out that reality is like a kind of music. And maybe you want to laugh me off the stage right now, but bear with me. Before quantum mechanics...
So guys, maybe we should talk about this. Why is this barely an analogy? What is the connection between the reality of electrons in the subatomic and music? Where's the connection? You guys know more about music than I do, so you should be able to come up with this. Because you pluck the string on a guitar, you hit a key on a piano, you're making music, but what are you actually making? Waves. You're making waves. Guys, literally, you're making strings vibrate. And even on like trumpets or things that don't have, strings that vibrate, there's something that vibrates, whether it's your lips into a trumpet or the reed on a clarinet or whatever that thing might be, something is vibrating. And the minute you've got something that's vibrating that makes music, you've then got electrons that, while they're not vibrating, they follow paths and they occupy volumes that are described by the same equations that describe vibrating musical instruments. And that tight connection seems like it's way more than coincidence. There's something wavy about our world.
Scientists envision the atomic world as just a miniature macroscopic world. Electrons seem to just be particles orbiting around a nucleus. In fact, there was a great Dane, Niels Bohr, yes. Like certain other people I might name, he sometimes felt like he was in the shadow of his older, more successful brother, an Olympic soccer player, while Niels's handwriting was so poor that he had to dictate his PhD thesis to his mom.
You guys know that about Hank? His brother is actually on the national team, the soccer team, and he makes YouTube videos for geeks.
Nevertheless, he was an ingenious physicist. Now, you might remember a couple episodes back when John Dalton determined that elements only exist in discrete packets of matter. Well, by Bohr's time, the same thing was known for the energy given off by electrons. That energy only came off in what ended up being called quanta, which is the root of the term quantum mechanics. In 1913, Niels Bohr came up with a simple model for describing these energy levels for a single electron in hydrogen.
Did you notice this, though? That in this equation, the numerator is actually not a 1. It's a z. But what is z for an element? The atomic number. So for hydrogen, it's 1, and it goes on from there. Understand, you can begin to solve this equation for multi-proton systems like helium and so on, but the math doesn't quite stay this simple. That's why we're only doing this for hydrogen, because for hydrogen, element number 1, Z is 1, and then it really does work. But we've seen that equation before.
Merely assuming circular orbits. So there is some truth to the framework of thinking of electrons as particles. However, when he or anyone else tried to apply this to more complicated atoms, they failed miserably. Long story short, electrons don't really behave like particles. They're better described as waves. So we've known for like 50 years that this is an entirely inaccurate way of visualizing an atom. Nuclei, yeah, you can think of them as solid particles, but not electrons. Electrons are wave-particle dualities. I think of them like a resonance in the universe, and just like with a single string producing multiple notes on a guitar, an electron can exist in a number of different harmonics. This isn't an analogy either. Quantum physicists actually talk about the harmonics of electrons. After a few years of trying to figure this stuff out, a couple of very smart physicists started to look at electrons as waves, standing waves. This makes a lot of sense even to us lay guys. When you swing a telephone cord in a straight line, there are a discrete number of nodes, depending on the tension and the frequency, or in better physics terms, energy you put into the system. The same thing happens to an electron around the nucleus. A standing wave is produced only at certain energy levels. Anything...
Guys, let this soak in, because this is actually really interesting. Why is it that the orbits, which we actually call energy levels, why is it that they can only have certain sizes? We call that quantization, right? It's the ladder versus the ramp. But why is it that these electrons can only occupy spaces, well, on average occupy spaces that have these definite radii? And guys, the answer is this. It's because of the waves that describe those volumes. And what you find out, if you've taken physics, you know that there's constructive and destructive interference. Do you know about that? If you've got waves that are moving together, they amplify each other. I don't know if I can do this. If you get the idea. If you've got waves that are moving against each other, they cancel each other out. Well, guys, if you can describe the wavelength of the border, if you will, of the volume that the electrons can occupy, given that this wavelength is a fixed distance, there are some radii at which these waves wrap around on each other and stabilize each other. But if this wave, as you see it's a wave, if you were to try to wrap that wave around a nucleus, and if the peaks and valleys don't line up with each other, they interfere with each other, and therefore the electrons can't be in that volume because the boundary of that volume actually sort of consumes itself, and therefore it's not allowed. We're not going to get into this math, but guys, this is actually the reason why there are volumes where electrons can be and volumes where they won't be, because if given their wavelength, they interfere with themselves, they're therefore not allowed because they collapse on themselves. Where if the peaks and valleys line up just right, you've got a strengthening of the wave, and that provides volumes where the electrons can be. Does that make sense? Yeah. It's pretty cool. I love this. I've never showed this video to an AP class after we've done it with a general chem class. It just so happens that today in my general classes, we watch these videos just like you did last year. And as I was watching this video, I was thinking, my AP kids need to see this. So I'm glad we're doing this.
Thing in between is not allowed. An Austrian physicist, Erwin, the tension in the frequency, or in better physics terms, energy you put into the system. The same thing happens to an electron around the nucleus. A standing wave is produced only at certain energy levels. Anything in between is not allowed. An Austrian physicist, Erwin Schrödinger, who you may have heard of because of his cat, is the first guy who developed a mathematical model where the electron was assumed to be a standing wave. Now it is time to move a little bit into the realm of metaphor here, because I'm going to tell you how I think of electron shells and orbitals, not really how they are. The music of electrons is not simple music. It's no three-chord song. It's like Beethoven, but with more rules. Hard, fast rules that can't be broken. In that way, at least, it's more science than art. Electrons exist in orbitals, a bit like the individual notes on a keyboard. But the orbital's tone isn't complete until it has two electrons in it. And orbitals exist in shells. The first shell just has a single orbital, an s orbital, which can only fit two electrons. That's why the first row of our periodic table only has two elements. They play a simple song, those two, and a song that every other element will build upon. The second electron shell, though, is physically larger and thus can include more than just the s orbital. A second sort of orbital with three different configurations is added, the p orbital. Instead of just being a single tone, the p orbital is more like a three-part harmony, with two electrons in each part for a total of 6. Those 6 electrons of the p orbital plus the 2 s electrons are the 8 electrons referred to in the octet rule, the desire for most of the lighter elements to have 8 electrons in their outer shell, just like a musical scale. This is often described in terms of fullness or satiation, as if the atoms are like devouring electrons, but I prefer to think of an incomplete electron configuration as a cacophonous symphony playing at different keys and different tempos. And the closer you are to harmony, the worse it is, until one final note chimes in, that 8th note, and everything crisps into full resolution. A deep, complex tone emerges and the atom settles into complete harmony, the harmony of the noble gases.
Does that mean anything to any of you? I got no musical background at all. You got, yeah? It's interesting. It doesn't mean anything. It's just interesting to me.
That's just how I think of it. And just like with music, there's a bit of notation to learn as well. It's important to know how to write out what we call electron configurations, a condensed way of showing exactly where all of an atom's electrons are. First, we write the number of the shell, then the letter of the orbital, then the number of electrons in that orbital, and repeat until we run out of electrons. So for hydrogen with just one electron...
And guys, you will have to be able to do this on the AP test. But understand that you won't have this, right, where we labeled 1 through 7 and S, P, D, and F. But you do need to be able to do this. You don't need to know the weird exceptions, like the electrons jumping between the S and the D when you get into the transition metals. But you do need to be able to do this for the fundamental ones.
It's 1s1. For fluorine, it's 1s2, 2s2, 2p5. Now, as we move to the third row, an interesting thing happens. The third shell adds a third kind of orbital, the 5-part harmony with 10 electrons.
Do you like the dog off to the right? Kind of makes me... You guys never noticed that, did you? It's the 6th d orbital. It's a poodle.
Of the d orbital. But you might be saying, there's still only 8 elements in the third row. What's up with that, Hank? It's all lies. I'm leaving. Okay, calm down. The atomic symphony composes itself in peculiar ways. Because building the 3d orbital requires a lot of energy, electrons actually go into the s orbital of the 4th shell, or 4s, before going into the 3rd shell's d orbital.
Remember when you learned that? That the s fills in then the d? Because the d is harder to form, higher energy?
This is actually a trend that continues, and to remember it, I just write out the following on a piece of paper. These are the orbitals we know in all of the shells that we've seen exist. To figure out what order to fill them in, you just draw a diagonal line from the top right to the bottom left as you go. So 1s...
This is the way I learned this in high school. It was horrible. We actually had to write this out every time we wanted to do this because they didn't show us how to link it to the periodic table. I didn't learn that till college.
First, then 2s, then 2p3s, then 3p4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on. Armed with this knowledge, you can write out the electron configuration for pretty much any element on the table. Iron, number 26, would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Now, there are a couple of elements that have weird electron shells, but you could just look it up on Google. An interesting thing about d orbitals and the even bigger, more electron-rich f orbitals is they don't really need to be filled quite as much as the s and p's, because they're literally shielded beneath the s orbitals of the next shell. The s and p orbitals I think of kind of like the trumpets and violins. It's really terrible when they sound bad, but the bass notes, deep and rich, hide a bit underneath the rest of the orchestra, just like the d orbitals literally hide underneath the s orbitals that have already filled above them. Yes, these incomplete orbitals affect them, but because they're shielded, these middle-of-the-chart elements are generally less reactive and happier to bump electrons along from atom to atom, making them conductive, or just hanging out together in big masses of electron-sharing lumps of metal. So why are orbitals useful when it comes to understanding how an atom is likely to react? Well, first, it really matters how much energy is required to remove an electron from an atom to form a positively charged ion. This energy is called ionization energy. If there are several electrons being removed, this is a stepwise process, starting with the electron at the highest energy level, or the outermost one. Since the outermost electron has the highest energy, there's the least energy necessary to remove it. More energy...
Did that make sense? Because this is actually the crux of PES, which we're going to learn Thursday. Let's do this again. So ionization energy, the amount of energy that it takes to remove an electron. So guys, which electron's going to come off first? One on the outside or one in the middle? Outside. Why? Here's the answer.
If there are several electrons being removed, this is a stepwise process, starting with the electron at the highest energy level, or the outermost one. Since the outermost electron has the highest energy, there's the least energy necessary to remove it.
Does that make sense? Because the electrons that are on the outside have the highest energy already, so it takes less energy to get them to zero or orbital infinity. They've got the most, so it takes the least to get them to go away. That's PES in a nutshell. We'll talk on Thursday.
More energy is needed to remove the second farthest one out, and so on. And of course, when all the electrons in the outermost shell are removed, there is a really large energy jump necessary to remove an electron from the next shell down, because that shell will be isoelectrically analogous to a noble gas. Just like how atoms are isotopically the same when they have the same number of protons and neutrons, atoms are isoelectrically the same when they have the same number of electrons. And just like there's energy associated with removing electrons to form cations or positively charged ions, there's energy associated with adding electrons, usually to fill an orbital to achieve a stable 2 or 8 electron shell configuration. Just like with the ionization energy, there's a discrete energy jump involved with the adding of an electron. That energy is called electron affinity. Now, are you ready for the real mind melter? If you're following along in your periodic table, which of course you aren't, you may have noticed a little something interesting. On the left-hand side, you have your s orbitals, 1, 2, 3, 4, 5, 6, 7, s.
You guys remember that?
In the middle, you got your Ds, 3D, 4D, 5D, 6D, and on the top right, 2p, 3p, 4p, 5p, 6p. And below, of course, in the little island of the lanthanides and actinides, your f orbitals, 4f and 5f. And so, with just a glance at your periodic table, you can work out electron configurations and elemental stability and the fundamental physical reality of the elements. That's why this thing is so beautiful to me, because when you get to know it, you see all those flawed, competing harmonies and all of the actions and reactions that occur because of them, changing their song into something more stable and powerful and eternal together.
Guys, did any of you have that experience last year when you learned this stuff and just found yourself thinking, this is way more ordered than it should be? Like, something's going on here. Kind of cool.
Making everything. Now, as I've gone through today's episode, I've described electrons mostly in musical terms as vibrating waves, harmonies in the fabric of the universe.
Okay, so guys, this is interesting. This will not be on the AP test, but if you were pushed for an answer, what is an electron? What do you say? Is it a particle? Is it a wave? If it's a wave, does that mean you've got a particle that's moving as a wave? Where do you go with this? Go ahead, Doug.
I'd say it's a particle that acts like a steady.
Okay, so you're picturing actually a thing that's moving. Yeah, and actually the answer is no. It's a common misconception, but that's not the relationship between the particle and the wave. Go ahead.
I would say that it is a particle that we do not know the place of, but the probability of it being in a certain place is understood as like a wave, like where it's probably.
All right, so let's try that. So it's a particle that you can't find the position of, but you can predict the position of it based upon structures, volumes that are described as being wave-like. Yes, but not quite all the way there. Go ahead.
So, like, when we watched that one video about the thing going through, like, the little holes,
Mm-hmm.
it was a Bohr video.
Yes.
And we talked about, like, how they have, like, all the possibilities of being only in certain places.
Okay.
And how the electron, like it could be in any of those places, but it couldn't be in between.
Yes.
I think that, like, an electron would have to be like, kind of like an attractive force. But, I don't know, like, that could only be in certain places. I don't know how to explain that.
I'm not. I don't even know, frankly, Jessica, where to engage in that. Yeah, but it's vague, right? There's probabilities, and there are places where we can, and places where we can't find them. But let's come back to this, and guys, this is the leap, if you will. It sounds like you're all comfortable to some degree with this idea of the wave-like characteristics of electrons. So, guys, let's try another analogy. Waves in the ocean. You can picture waves transferring through the ocean. But, guys, when a wave passes through the ocean, what is waving? Physically, what is propagating that wave? The water, right? So, guys, if that's the case, and if you add energy to water and it makes a wave, imagine throwing a rock into a lake. If the lake is still, you throw in a rock, it adds energy, and it creates waves, right? But it's the water that's simply transferring the energy. So the wave is the manifestation of energy going into a medium. You get the idea? What is the medium that's carrying that wave that we think of as electrons? And guys, there's an answer to that. It's called the electron field. Guys, throughout our universe, there are fields. We describe them as fields. There are gravity fields, there are electron fields, there are fields, and when you dump energy into this field, you end up with waves. And those waves can then, if we study them, transition to particles. But left on their own, the way that we understand electrons is electrons are energy being dumped into the electron field that creates a standing wave. And we can fully describe that electron as being a wave. But then if we try to study that electron, it takes on a particle-like nature, and the likelihood of us finding that electron at any given moment is described as the minimums and maximums of that wave. But that wave is actually simply what we call, it's energy being transferred through this thing called the electron field. And Hank takes a shot at this as well.
That's indeed how I like to think about them. But of course, that isn't a complete story. And I have gotten sick of people telling me that the human brain is incapable of imagining the reality of the subatomic. So I'm actually just going to serve up a big heaping pile of reality on you right now, no matter how odd it turns out to be. There are a number of everywhere permeating fields in our universe. One of those is the electron field. In order for an electron to exist, there has to be an excitation of the electron field, and we can describe those excitations as waves, just as a wave in the ocean is an excitation of the water. At any given moment, the electron can be anywhere within the function of the wave. But waves are defined not by harsh boundaries. Instead, they're strong in some areas and weak in others. The strength of the wave at one certain point in space determines how likely it is that you will find the electron there at any given time if you measure. And so, if we're trying to understand reality, we should not think of electrons as circling around the nucleus of an atom like planets around a star, but instead as an excitation around the nucleus. And the shape of that excitation is the orbital. Orbitals are precisely the reason that everything exists. They are the root and the key and the nexus and the crux and the keystone and every other metaphor of not just chemistry, but existence. Thank you for watching this episode.
What do you think? Go ahead, Doug.
So, to clarify,
Yeah, please.
the electron field would be like a pool of water wrapped around the nucleus.
Yes. Yes. But it's not matter, right? But it is, stretching the analogy of the water wave, this electron field is the water that accepts the energy and in which the wave exists. Yeah. It's and guys, I like the way he described these as everywhere permeating. That guys, right now, even in empty space, but everywhere in our universe, there is this thing called the electron field, and excitations in that field cause electrons to exist. Yeah.
I was wondering, like, is he saying that the electron field is
It's everywhere. It's however big the universe is, and there's arguments about that, but however big the universe is, that's the size of the electron field. It is literally everywhere. There are these fields that just exist throughout it. You can't see them, but when energy enters into them, we end up with the probability of electrons that then physically become particles when we interact them by studying them. Potentially, yeah, because these electrons definitely interact with each other, right? That's why they take on these complex shapes. Yeah. Exactly. Yeah, go ahead, Elisha.
So what determines
Exactly. That's a brilliant question. So what determines, what separates it? So it's all the same field. So maybe another way to ask the question is, what determines the waves, right? Which, is that what you're saying?
No, like what determines the energy levels? Like, because you can't just go from N1 to N3.
Right, and actually your question and what I said not well are the same thing. So what determines these energy levels? And the answer is I'm just going to hit play. This. So this is actually what determines the size of these energy levels are the sizes, if you will, at which these waves become self-reinforcing. That if the peaks and valleys don't line up for these waves, they actually cancel each other out. They become self-destructive. And that would then be a volume that would not be allowable given the size of that wave. But where these waves, and these should actually be different sizes. We should have smaller and bigger. And your book actually shows them as different sizes of waves. That's where the electrons can be.
So it's basically just like the frequency.
Not frequency, wavelength. But they're related, right? But yeah, if you think of it as frequency, that's acceptable. Yeah, no problem. Guys, we're going to give this a couple more. I know this is fascinating, but we need to get to the what do you need to know. So yeah.
That's kind of fast, but like for you're doing the rock in the water analogy.
Yes.
So the rock is like the nucleus, and like when you drop it.
No. So I love what you're thinking, Jeanette, that you drop the rock in the water, and where the rock entered the water is the middle, which then might become the nucleus, right? But that's not the case. The energy is not radiating out of the nucleus.
Like the second analogy with like gravity, like if the sun was the nucleus, and I know it's not right because it used to be the Bohr law, which I feel like kind of would be like that.
Yeah, so don't try to make those connections, or perhaps the connections are dangerous of trying to think. Don't take this water wave analogy too far. The limits of the water wave analogy are that that you have an addition of energy which causes a wave, which then we think of as being a boundary. But understand that's where the water wave analogy stops. The waves that exist in water are not the same shape or function as the waves of the electrons. So you don't think middle, because that gets dangerous. You guys okay? Let's do a couple more, yeah.
So with this, it's like the constructive versus like
Yeah.
destructive interference, is that why only certain energies are allowed to push it to different?
Exactly. Because say, for example, and I'm fearing to touch my board, so I'm not going to, but say that we added enough energy, and this one should be bigger. This should be the 5th energy level, and they didn't do a good job of that. But say that we added enough energy to kick this electron to like the 4.5 energy level. Well, it still has the same wavelength, but if you were to stretch that wave around the nucleus, it wouldn't line up peak to peak and valley to valley, and it would be destructive, and as a result, the electron couldn't be supported there. So it's only supported at this radii that then provide constructive interference in the waves as it orients around the nucleus.
Right, so when you're trying to like move an electron up
Mm-hmm.
in
Yes.
you
Yeah.
can only move it like a certain amount, like not more or less.
Yes, exactly. Because if you did move it more or less, you would be creating destructive interference in their wave patterns, and they just collapse back to the lowest, closest, stable spot. Yeah.
Okay.
Yep. Go ahead.
I have a question about that then. So if you gave it like not enough energy to jump to the next one,
Mhm.
does it actually leave the orbital and come back?
Yeah, absolutely.
Like,
But
if you had like a bunch of them going
what you would experience is nothing.
so it would nothing would happen. but
Correct.
It would actually be leaving the orbital for a second.
And no, and that's it actually doesn't. No, and we're not going to talk about why. But it's almost as if the electron knows how much energy it could absorb, and if it's not there, it doesn't do anything.
Where does the energy go? Like if it's not going into the, because like it's not jumping to the next,
Yeah, it would either pass through, or if it were absorbed, it would then be re-radiated as light. Yeah, and that's the whole idea with the absorption spectra, that the energies that cannot be absorbed are not being kind of absorbed and then given back. They just pass through as if they'd never interacted.
So if it's light and it would be dropping them when it drop to another.
Mm-hmm. Yeah. Yes.
Yeah.
Hi. What? Oh. Do you mind just leaving it outside my door?
Yeah, I know.
Thanks. Mark, finish up for us.
So I'm trying to the
All right.
So if we're going off of the Big Bang Theory,
Oh, sure. Go there. Yeah.
could we like say that like that the Big Bang was like the rock where the energy added into the water, and then that energy is flowing outwards, causing energy to go like to continue to move outwards, and then energy causes the electron form, like in that
I have no idea. I have no. So, I mean, it sounds like the question that you're fundamentally asking is, how did this electron field originally form? And how does it relate to the Big Bang and what we're experiencing from that time zero? I mean, I don't know the answer, but I don't know if anybody knows the answer.
Look at quarks.
Look up quarks?
Yeah, quarks.
How is that?
Well, I mean, it's kind of a huge theory, but people say that the origin of the universe came from quarks coming together forming clouds, and eventually that cloud expanded until it just went bang, formed, stars and stuff.
I'm not familiar. So if you don't know what quarks are, guys, there are these things called fundamental particles. They're particles that can't be cut down anymore. Electrons are fundamental particles. They aren't made of smaller bits. Protons and neutrons are not. Protons and neutrons are actually made of smaller pieces called quarks. But the connection between that and what Mark's asking, I'm not familiar with. So, guys, you ready to get into where you'll be held responsible for this? Guys, it actually goes like this. Let me quit out of here. Let me grab this. And then, guys, if you need refresher on this, feel free to print this slide. We're not going to directly relate to it, other than to say that we understand that the Bohr model is not actually correct. That while, yes, these electrons do occupy energy levels, and these densities defined by the 2n squared rule. And now we know, guys, that as n increases, right, this n is the denominator of the equation we just solved to figure out the energy of energy levels, that as n goes up, the size of the cloud increases, the energy increases to a maximum of what? What's the maximum energy? 0, right? So as n goes up, the cloud gets bigger, the cloud has more energy to a maximum of 0, and the capacity increases by the 2n squared rule. Remember, 2 and then 8 and then 18 and then 32. But guys, these energy levels are broken into sublevels. That tells us the shape. The shapes of these are the S's, the P's, the D's, the F's. Then these sublevels are broken into orbitals. Guys, how many electrons can go in an orbital? 2. And what do you know about the 2 electrons paired up in an orbital? Opposite spins. And guys, what does spin tell us about the electron? The orientation of what? They're poles. Remember, guys, while electrons are electrical, they are also magnetic. They literally have north poles. And when 2 electrons pair up in an orbital, they will orient oppositely so that their magnetic poles are aligned opposite of each other. And this allows them to pair in an orbital where otherwise they wouldn't. So guys, with all of these ideas pulled together, we can then talk about the structure of atoms as it relates to the periodic table and energy levels and sublevels and orbitals. And guys, don't try to write any of this down because you're not going to have time. So it goes like this. This is the nucleus of the atom, and these rungs represent the energy levels 1, 2, 3, and 4. Guys, what is wrong already with my picture here? Where should the nucleus be? Like down on second floor. Guys, proportionally, and you can see this here. I tried to draw it so that this space is bigger than this. They're always getting closer together, right? And we understand why mathematically, because the denominator of the fraction that tells us the energies of these things is the energy level squared. And that squared relationship predicts that these are getting ever closer, but proportionally the nucleus should be like down in Ellingford's room. It should be down there, but then I couldn't draw it, so I just brought it up. So then, guys, we can predict the number of electrons in these energy levels, and it goes 2 in the first energy level. How many in the second? 8, 2n squared, right? How many in the third energy level? 18, 3 squared is 9, times 2 is 18. How many in the fourth energy level? Third. Do you guys not remember the 2n squared rule? So the equation that predicts this is the 2n squared rule. So you plug in 1 squared is 2, times 2 is 2. Plug in 2 squared is 4, times 2 is 8. Plug in 3, you getting the idea? So when we plug in 4, how many electrons will be in the fourth energy level? 32. Is that okay? Okay, then guys, we break the energy levels down into sub-levels. There's one energy level. Is this coming back to you? One energy level in the first, one sub-level in the first energy level. It's an S. There's 2 in the second energy level. What are they? S and P. 3 here, SPD. 4 here, SPDF. Is that coming back to you? So then, guys, we started to play this game. We said the first energy level contains one sub-level. It's the 1s. It contains 2 electrons. Then we said that that's a circular orbit, and that's the 1s orbital. Then we went to the second energy level. We said that contains 2, a 2s and a 2p. There's 2 electrons in the s, so how many had to be in the p? 6. And if an orbital holds 2 electrons, that means we need 3 orbitals, and that's where we get the dumbbells. Do you remember that? So now we've got a small 1s, we've got a bigger 2s, and then we've got these 2p's, which are then dumbbell shaped. Hey, hey, how are you? That actually goes, what's her last name? No, down to biology. So, Harvard. Yeah, that actually goes down to her room. Okay. Thanks, Young. Okay, so guys, now we've got the 1s and the 2s and the 2p. And remember, the p has got 6 electrons. That takes 3 orbitals to hold those. But when we bring those all around the same nucleus, remember when you had this aha moment? And so, guys, what we learned then is that in this 10-electron system, here's the 1s, here's the 2s, and then the 1, 2, 3 2p's, and that would be what actually neon looks like relative to its orbital structure. You guys remember that? Thoughts or concerns or questions? Or you go ahead.
I don't know. We just thought it was neon on the left.
It could have been. You don't like it. All right. But guys, let's make sure you're clear on this. So what is it that you're actually looking at? So if we think that neon looks like this, what are these clouds? What do they represent? Who said the magic word? I heard it over here. Go ahead. Go ahead. What do these clouds represent? Guys, they're probabilities. These are the places where you will most likely find these electrons at any given moment in time. So the first volume of highest probability is this sphere. Then the next highest probability is the 2s. And then you've got these 3 regions of highest probability that are the 2p's. But understand, this is not where these electrons are. These are the regions of highest probability. These boundaries are actually representative of the excitations in this electron field. But if we go to look for these electrons, this is where they tend to be. And as a matter of fact, they tend to be there so frequently that this then describes the shapes of these atoms that then leads to the shapes of the molecules when they bond together, and all the stuff that we can predict from here on out about electron structures and bond angles and molecular geometries and all of that other stuff all links back to this. So while it sounds sort of wishy-washy in clouds and probabilities, guys, this does in fact describe their three-dimensional structures, which then leads us to molecular structures, which is where we're going next. So you good on the idea? Go ahead.
So, you know how, from like the 1s orbital is just like a sphere?
Yeah.
But there's 2 electrons in there, right?
Yeah,
So do they-
Or there can be 2.
Right.
There could only be 1, but keep going.
Assume there's 2, then
Yeah.
are they like always gonna stay like opposite of each other?
So when we're thinking them as waves, it doesn't matter. But when we locate them as particles, and guys, Luke's question was, will they be spread out as? The answer is yes. When they take on that particle nature, they do try to stay apart from each other because they're literally they're negatively charged, and like charges repel. So when they take on that particle-like quality, they will spread out as much as they can. Go ahead.
So when we watched the Nova video,
Yes.
had
Yeah. Yeah.
it had like, it said you have to like put it in a charged thing to really know its orbit, because like when it's in there, it like doesn't have like a definite orbit. Like it's
Yes.
all over.
Yes. Right.
So how do we like determine that they're like opposite?
That's a good, so go back to the thing that you said. You were saying we have to put them in a, did you say charged field, in order to define their orbits. But what that external charged field does is that's how we locate. You know, we've said electrons are waves until we study them. Well, how do you study them? Well, you place them in charged fields, but what that charged field does is dumps more energy into the electron field and forces them to pick a place. And so that's what they were saying, is it's a different way of thinking about how do we study electrons, because it's that process of study that forces them to choose where they're going to be. And as soon as they choose, they will choose to be as spread out as they possibly can, because now they're taking on the characteristics of particles with negative charges. You guys okay on the ideas? So guys, let's do this then. So moving on up the rungs, we move into the third energy level. And guys, the third energy level has got 3 sublevels, the S, the P, the D. There's 2 in the S, 6 in the P, and then the remaining 10 in the D. And remember, when we look at these orbitals, there are in fact 5 d orbitals, as this amazingly simple progression suggests. That there are 5 d orbitals, and these d orbitals again represent the volumes where these electrons will likely be. But remember that when we bring in the fourth energy level, these wacky d orbitals are hard to form, and so as a result, the 4s, even though it's bigger, it's lower energy. So these are in order by energy. The 4s is actually bigger, but it's lower energy because it's a simple sphere. And as we go up, then we've got the S, the P, the Ds, and the Fs, and they progress from there. Do you remember the pattern? Okay, so guys, from this pattern then, we realize that this then maps directly onto the periodic table. If the horizontal rows go 1 through 7, and if these are the S's and these are the P's and these are the D's and these are the F's, and they are, we can then figure out the electron structures for all the elements on the periodic table just by locating them and then counting up to them. But guys, so that you know, the one that you've got to be able, the only one of these that you've got to be able to do is the 1s2, 2s2, 2p6 stuff. So like, for example, if we were to do carbon, we've got the first 2 electrons in the 1s, then the next 2 electrons in the 2s, and then 2 electrons in the 2p. So we would then write this 1s2, 2s2, 2p2, and that would be carbon. Remember how that goes? Yeah, and actually you'll see that they'll do that like on the AP test. So like, let's, for example, if we were to do aluminum, what we would do then for aluminum is we would go, so, and that's what you're talking about are noble gas abbreviations. So if we were to do aluminum, we would go back to neon, And then in addition to neon, we would have the 2 electrons in the 3s. So we would go 3s2, and then we'd have the 1 electron in the 3p. So that's the way we would represent neon. Yeah. So guys, the one thing that tends to throw people for a loop is, for example, if we did, let's do zinc really quickly. So zinc would be argon, and then in addition to that, we'd have 4s2, and then 3d, and that's all the way full, so that would be 10. Is that okay for zinc? Do you have questions on that? So guys, what if we did this? What if we did zinc plus 1? Which electron would we take away? It would be this one. So this would become 4s1. Remember, never add or remove from the d sublevel because those are never valence. Okay. So guys, that's really the thing that you need to remember from this, is how to do noble gas abbreviations and things like that. So questions about that? You guys okay? Okay, so go ahead.
But even the orbital, that's the highest.
Yes, absolutely. So for example, let's say that let's just do aluminum again. So aluminum would be neon, 3s2, 3p1. So if we wanted to go aluminum plus 1, we would take off that one. If we wanted to go aluminum plus 2, we'd take off one of those. Aluminum plus 3, they'd all be gone, and then we'd have the electron structure of neon. Is that okay? Yep, always the highest S and P. So you guys okay? Okay, so guys, understand we'll have plenty of time to answer your questions on Thursday. I'm sure questions will come up. Guys, here then is your homework, and take a swing at these tonight and tomorrow, and then guys, we can ask and answer questions when we get together again on Thursday. And then we're going to get into hold on, don't do that, do this.